So this lecture is about quantum information theory. And I guess most of you have heard about this at least a bit, but let me motivate this a bit more. So if we think about information, then we often have to think about a carrier of information. Because if I want to give you some information, you need a carrier, okay? And I think a very nice example is if I want to share some music or if I want to store some music. Okay? What I do is I have a music track and I encode it into a carrier. So we do an encoding. Say the music track is some information M, and then we do the encoding, say, on the tape, and then this is T of M, okay? Our information is now T of M, which is on a tape. And then I probably share this with you, or I send it somewhere, or I store it. So there's some sending or storing, such that my information is now T prime of M, okay? The reason is that possibly something happened to my information such that I got scratches on this tape or something disturbed this whatsoever. So possibly this information changes within time. I mean, if you store your tapes for 10 decades, for a few decades or so, like if you listen to the tapes of your father or your mom, then you're not getting back the same information as they encoded, right? Because something disturbed this information. And what you then do is you do a decoding and first a measurement and a decoding. So it's measurement and decoding. Okay, now my drawing's getting bad. And what you get out is some information M prime now, okay? So this is completely classical picture. We store some information on a carrier, we do something with it, and then we measure and decode it, and we get out some different information. And now the challenge is that this information M prime should be as close as possible to M, right? This is the challenge of our industry, and in addition to our industry, the challenge is that they have a convenient information carrier. Okay, that's why we went from LPs on vinyl to some tapes and now to very small devices. The reason is that we can get back M prime better with a more convenient device. Okay, so this is the challenge. And now if you see what our industry does and our technology is that we're going even smaller and smaller and smaller. So our information carriers are getting smaller and smaller. And at some point we are so small that we really have to think about, okay, what's happening there from a very fundamental point of view. And that's where quantum mechanics pop in. So in your quantum mechanics lecture, you heard that if you go smaller and smaller, at some point we better describe the system from via quantum mechanics, right? And now we can ask the very same questions here with quantum mechanics. Namely, we can have some information, M, and we now encode this into a quantum state, say rho m. Okay? And this quantum state is also then evolves. For example, we send it from party A to party B, or we store it somewhere. So it's again sending, storing, such that we have rho prime of m. Okay? And if, for example, you send me some information on a quantum state, okay, what I'm going to do is I want to get back this information. So what I do is I perform a measurement and I decode it. So I make a measurement. and I decode it in order to get back the music track. Okay? And this is now the very same thing. So we start from an information, it's distorted, and we want to get back the information as good as possible. And in quantum information theory, it's a very typical question to consider such settings and ask, okay, which channels, we call this channels, okay, which channels act on my state and how do they act, and which channels are such that I can get back as much information as possible. Because M prime is not exactly, in most cases M prime is not exactly M, right? And then we can ask, okay, which processes affect my state and at which point do I get back enough information? Okay. So these are very typical questions, and you can think about this in very different perspectives. Also, a typical thing is, okay, a distribution of information is here. It's not typically music, but say we want to communicate with another party via quantum states. So we encode our information in quantum states, send it to another party. They do perform a measurement, and then we can ask, okay, how much information can they get out of their measurement, given that there's some noise in the transformation? Okay, these are very typical questions in quantum information theory. So from this, you can already see that quantum information theory is more or like a theory where we study the state space in very general, from a very general perspective. So it's more a study of the Hilbert space, so to say, and our states at the Hilbert space. And with this, we study with respect to some computational advantages, for example. Okay, this then goes into quantum computation, where we ask, okay, can we perform some computational tasks better if we use quantum states instead of classical states? Or if you go to quantum communication as a motivated, okay, can we have some communication protocol where this allows us to communicate better, for example, to communicate securely? Okay? These are very typical questions. So, and this is, you can boil it down to a study of the state space. This is, in the end, what quantum information theory is about. And this brings me now to the outline, what we're going to discuss now in this lecture. So you can see it more or less as an introduction into quantum computation and quantum information, right? So I cannot go into detail in both fields because this lecture is limited, but I'd like to give you an overview at least, and I'd like to go into some details, right, that you also see, okay, what is it about? I don't want to be very rough and without anything detailed. I really like to go into some parts in more detail. And we are not going to prove everything here. So this is a theory lecture, and we are not going to prove every theorem that we state. But for those which we do not prove, either you can find the proof in the manuscript, or I have a reference where you can find the proof. So those of you which are interested can really dig into the literature. And I also like to I'd like to motivate you to read books alongside this lecture, right? So please don't see the script that I put on Ilias as a book that you can, with which you can really go into this topic. I mean, this is something that helps you, right? But you should really take books and try to read it, which is good if you really want to go into this topic a bit deeper. So now comes the roadmap of this lecture. So first, what we're gonna do in the first few weeks is we're gonna recall some stuff that you probably heard about and add something more. And this is about the formalism. So the formalism is, of course, in the end, linear algebra. So we're gonna recall some stuff that you know from linear algebra. We're gonna also discuss some more things that are relevant for quantum information theory. I hope this is gonna be not too dry for you. So please don't be yeah, so please be patient, because the first, let's say the first week or the first 2 weeks may be a bit dry with a lot of definitions and stuff, but then we soon reach a point where everything gets really interesting, but we really need this basic fundamental things in order to dive into quantum computation and quantum information. So there, what we're gonna discuss is like Hilbert space and Dirac notation. We're gonna see what are operators, especially linear operators. Then we're gonna dive into evolutions and measurements. And then we briefly discuss Bell's inequality, which means that we do a very brief introduction to entanglement here, and just to see, okay, what is Bell's inequality, what does it tell us? And then we go into the our actual topics, which is quantum computation. In quantum computation, we're going to discuss, okay, what's a qubit, what are quantum gates, okay. Then what's a universal gate set, we're going to prove that there's such a universal gate set, and then we go in with having this studied, we're going to see some quantum algorithms. So we're going to study some quantum algorithms, and yeah, that's it. That's the first direction, and the second direction that we're going to go is more quantum information. And there we first going to discuss, okay, what are quantum operations, which is exactly this here. So what I called sending or storing. So we describe this by very general by quantum operations, also called quantum maps. Okay. Then we discuss distance measures. Okay, distance measures. With distance measures, we can quantify how much this rho pi m is different from rho m. And then we're going to quantify information. Both are going to give there an introduction into classical information and then quantum information, which is called entropy of information. And if there's enough time, we're going to do some entanglement theory. So there I'd like to give you an introduction into a theoretical approach to entanglement. Okay? So if we discuss Bell's inequality here, it's going to be very rough, just a pure bipartite state. We're going to say what is entanglement there, but we're not going too deep further. And if there's enough time, we're going to do it here. And then there are some topics which we can discuss if there's some more time. This is quantum communication. And on this side, it's quantum error correction. But I'm going to discuss these two topics if you really like to discuss this and if there's enough time. I think it's better to the other topics and make it, at least understand them a bit more in detail instead of going through too much topics. Okay. Okay. With this, I hope that I gave you a little bit of a motivation to start with our first part, which is the formalism of quantum information theory. So we're going to now set the stage introducing Hilbert space, Dirac notations, linear operators, and so on. So this is going to be, as I said, a little bit dry in the beginning, but it's getting better. And this is going to be the first, I don't know, 2 or 3 weeks, and then we go first into quantum computation and then quantum information. Okay. So we're going to start now with the very beginning, because I want every one of you to have the very same chances to understand everything. And the very beginning is postulates. So the first chapter, which is the formalism. And our first section is going to be Hilbert spaces and Dirac notation. Okay, as promised, we start from a postulate. So we have postulate 1, which says that every isolated quantum system can be associated with a Hilbert space. Or we possibly, instead of quantum system, we can also say physical system. Okay. So we denote the Hilbert space by H, and it's also known as state space. And this is a complex vector space together with an inner product. And then, if you care about the states, then we know that a system is completely described by a state of the Hilbert space. By a state, say psi of H. Or a density operator. So first, we're gonna discuss a bit more states. of the Hilbert space. And at some point, when we introduce linear operators, we're going to see what the density operator is. And then there we're going to learn that actually, in order to describe the state of a physical system, we better use density operators, right? But so far we're going to restrict to pure states, so states of the Hilbert space. And okay, so this is our first postulate. And now a few things as a remark. The first thing is that we restrict to finite dimensional and discrete Hilbert spaces. So if it's an n-dimensional Hilbert space, you can see it as c to the power of n. The reason for this is to make our life easy. It's going to be hard enough, you'll see. But once you go to infinite dimensional Hilbert spaces, everything becomes very hard. And you possibly have studied some infinite dimensional Hilbert spaces at some point. I think in don't know, linear algebra or mathematics 2 or quantum mechanics.
That's my question.
Yeah.
Your element should be
Sorry. Okay, thanks. Then second point is that we're going to denote, or say like this, we use Dirac notation. And write our states as in this cat version, okay. And it has a dual vector, which we write as a bra. Okay. Then next is about this inner product that we have here together with our complex vector space. And the inner product is written as follows. So for psi and phi, we write the inner product as either phi psi or cat phi, cat psi, or very short as phi psi. Okay. We mostly use here the latter notation, the last one, but at some point we also use these notations here. But they just rarely appear, so mostly gonna stick on this one. And then the inner product also induces a norm. So the product induces the norm psi, the square root of the inner product with itself. And we also say that the state vector psi of h is also called simply vector state or cat. So there are many names for these elements of the Hilbert space, and we're gonna use. I think I'm gonna use everything like state vector, vector state, or cat. Okay. I think most of the time I simply say state, but I hope that you know what I mean with this. Okay, should make it clear. And then with this formal introduction of a Hilbert space, we now have our inner product. And now we can think about, okay, what do we need if we want to calculate in such a space? Okay, what we need is a basis. So this brings me to definition 1. which is that the basis of a d-dimensional Hilbert space is a set of linearly independent vectors, say v1 to vn, such that any state vector v in H can be written as equation 1.1. So we can write this as a linear combination of our basis states. And the elements Hij are complex numbers. Okay. And now if additionally if these basis states are additionally orthogonal and normalized. So there's a mistake in the script, sorry for that. If additionally they're orthogonal and normalized, then v1 to vn is called an orthonormal basis. We simply say an ON basis. And our vector v has the norm 1 if and only if the components, so the modulo square of the components, sum to 1. So this would then be a normalized vector. And if not stated otherwise, we usually always consider our state vectors to be normalized. Right? And we also usually always work with orthonormal basis states, because this makes everything very easy in the end. So at some point it happens that states are not normalized, but then I think I'm going to say it explicitly. Okay. So we have now a Hilbert space, and we have a basis of this Hilbert space, possibly known an orthonormal basis. We can now ask, okay, how can we represent now these states? Because we said, okay, the Hilbert space is a complex vector space, means that our elements of the Hilbert space we must be able to represent them by complex vector. That's what we're going to do now. So say that we are given an ON basis. And what we're going to do is now we choose a representation. So this is very important to understand that these are formal objects, and we now choose a representation. Say, for example, so this is now an example. It's I think the most convenient and the typical example that we say, okay, our first basis state is 1. The second basis state has only 0 entries except the second one, and so on. Okay? So now we chose a basis. And with this basis, we can now represent our state vectors. So then we can write psi, which we know that we can write as a linear superposition so we can write this now in its matrix representation. Then psi, say, reads in the matrix representation. Okay, the dual vector. So the psi is one column, the dual vector is a row with complex conjugated elements. This is equation 1.2. And suppose now we have two state vectors, psi and phi. Then the inner product in this, given this representation, we can now perform the inner product. Let's make it explicit. So we have phi 1 to phi n times psi 1 to psi n. Okay, now do matrix multiplication. What we get is sum of phi j star times psi j. Okay, equation 1.3. And let me also now introduce the so-called outer product. So this is now the so-called outer product of phi and psi. You see that this, the inner product gives us a scalar. So this is, so to say, a complex number. And the outer product gives us, so to say, a matrix now in this matrix representation. So what's important here is that you understand that the Hilbert space itself is a formal space, okay? And only if we choose a basis representation, only then can be represented via a matrix, okay? So if you do some programming, if you want to simulate something, what you do is you always have to choose a basis representation in which you can write down your states of the Hilbert space, okay? And here let me do an example. So let's consider the so-called the Hilbert space of a qubit. Okay, a qubit is simply a two-level system. So we have as a Hilbert space, we have C2, and let's choose a basis. Okay, because we now want to represent things, we choose a basis, and first of all we have to consider an ON basis, and the typical ON basis of a two-level system is written down by 0 and 1. Okay. Now we choose a representation. Say 0 is the vector 1, 0, and 1 is the vector 0, 1. And now we can, with this, we can now write down different outer products. For example, say 0, 1, which would be, let's say first 0, 0, which would be 1, 0, 0, 0, or 0, 1, which would be 0, 1, 0, 0, 1, 0. So that's equation 1.5. This is now just an example, okay? We have a Hilbert space, we have an ON basis, an orthonormal basis of a Hilbert space. Then we have our representation, such that we can write these things down here as a matrix representation. And another example for a Hilbert space, for a basis, would be, for example, the basis of the so-called plus and minus state. Let me add this here. You're going to do this as an exercise, so this is on the first exercise sheet. So the plus state is 1 over square root of 2, 0, plus 1. And the minus state has a minus here. And it's easy to show that the plus and minus state are also an orthonormal basis. Okay? And you're going to, in this exercise, you're going to use this representation in order to express these states and some outer products of made by these states. Okay, just to get a little bit into the formalism. Okay, should we do a break? Now it would be time to do a break. Yes, then let's have say 5 to 10 minutes, so we meet 10 minutes after 1 o'clock or 1:15. Okay, thanks. So what we've done so far is very simply introduced Hilbert space, a basis, and we've seen the matrix representation. We now continue with operators. So the next thing is what we're going to do. We're going to study operators, and since quantum mechanics is linear, we're going to study linear operators. So section 1.2 is operators in Hilbert space. And we start with linear operators. So this is a definition. A linear operator A on H is defined to be linear in its inputs. So if we have A, the input of A, so the argument is some linear combination, say Aj of some state vectors Vj, then it's defined to be linear in its input, so we have sum over J, Aj, A of Vj. Equation 1.8. Okay, now some remarks. The first thing is that the matrix multiplication is linear, right? So, meaning that a matrix A with components AKJ is linear, meaning that if I have A, this is a matrix, and now this is a vector. Okay, now think of this as a vector. By a vector I mean a column with, say, n entries, and then the matrix multiplication is linear, such that this is sum over j, aj, and then a multiplied with this vector, right? So I can leave out, so I can put away this the parenthesis here because I consider matrix multiplication. Second is that any linear operator has a matrix representation. Okay, so every linear operator A has a matrix representation. Well, and to see this, in order to see this, say that A acts upon some state aj, vj, and then now say it's not different to say A acts on the state vj, okay, then this is again an element in the Hilbert space which we can write as a linear combination of our basis states. Namely, we can write this as j with some coefficients that I write down in a second, vk, okay? And let's say these coefficients are a, k, j, okay? So here's our linear operator, takes as an argument an element of the Hilbert space, and what we get is an element of the Hilbert space, which we write down in our basis with basis elements a, k, j. And these elements are our matrix representation. So the matrix with elements a, k, j is the matrix representation of A. And you can see it. So if you go from the left now with vk, and then we have A of vj. Okay, this is what we wrote down here. Our linear operator takes as the argument this basis state vj. Okay, and then we do an inner product with vk, and we can now write down this here. So we have sum over j, a, k, j, v, j, vk. Okay, this is nothing else but the delta jk. So we find that this is a. Sorry, now I did a mistake. Okay, no, that's correct. Okay, here. K prime A J K prime. Now it's correct. Okay, so we see that the element AKJ is nothing else but the inner product of VK with A argument VJ. Okay, and this brings me to remark 3. So what we see now is, on the one hand, every linear operator has a matrix representation, and on the other hand, every matrix can be written as a matrix with matrix multiplication can be written in this way. This means by point 1 and 2, we simply write that A acting on vector V as A V. Okay. So we drop this parenthesis, which is the argument. This is we can do for because the operator is linear, right? And then this kind of looks the same as if we do matrix multiplication. Okay, so now say we are given an ON basis and the entries A, Kj of A in the spaces then we can write it down. We can write down A in the outer product representation, and then the outer product representation of A is so what we've done now is actually introduced the matrix representation of linear operators. And now given a basis, a particular basis, we can express now this operator in this basis by this outer product representation. So this V's is the basis, and AKJs are the matrix elements in this basis. Well, from point 4, we have directly one consequence, namely, if AKJ is something like delta Kj, okay, then this is the identity matrix, right? And we see then that we get the identity matrix for every basis in the following form. So we have for any ON basis. Let me now write this as W. Okay, it's simply one choice of an ON basis of H. The identity matrix reads sum over J and then Wj. Wj is equation number 1.11. And this is called the completeness relation. Okay, so this is a direct consequence of this outer product representation. If AKJs are the delta Kj, then we have the identity matrix, and since this holds for any basis that we choose, we can choose any basis and write down our identity in this way. This is a very important relation that we use often, really often. Okay, at this point, let me do now an example. So suppose now we again consider the Hilbert space of a two-level system, and suppose again we have the basis which is built from the orthonormal basis states 0 and 1. And now suppose that we have consider an operator x, okay, and this operator x, we can now express it in the basis as x0, or if x acts on 0, then it's x0, 0, 0 plus x0, 1, 1. And if it acts on 1, we have x 0, 1, 0 plus x 1, 1, 1. And what we want to do now as an example is we want x to be the so-called Pauli x operator, which switches simply 0 to 1 and the 1 to 0. Okay, we're gonna see what the Pauli operators are when we discuss quantum computation in more detail. But so far, suppose simply that we consider now this operator. So this thing here is 1. This thing here is 0. Sorry, this is here 0 and this is 1. And this one here is 1 and this is 0. So means that we can express this now in the following form. So we have x equals to sum over jk from equals 0 to 1, x jk, and then we have kj. And what is it? If we plug all these numbers in, then we have 0, 1 plus 1, 0. Okay, so this is now in the outer product representation. And we can check these identities if we act with this now on 0. Okay, let's plug this in. Then we have 0, 1 plus 1, 0, acting on 0. It's nothing else but 0, 1, sorry, 0, 1, 0 plus 1, 0, 0. Okay. This inner product 0. This is 1. Okay, and this is exactly what we required here. And I mean the same thing if it acts on 1. So we have 0, 1 plus 1, 0 acting on 1. Something like 0, 1, 1 plus 1, 0, 1. Now this here 0 and this here is 1, so we get 0. And now in order to express this operator x in a matrix representation, we have to choose a basis. So we choose the basis. 0 is this vector and 1 is this one. Then x can be written as 0. Okay, let's do it step by step. We have 0, 1 plus 1, 0, which is 1, 0, 0, 1 plus 0, 1, 1, 0. Okay, let's see. This is a very simple example, just to get a bit familiar with the formalism, right? To do some calculations with inner products, to get an outer, to write down an outer product, and so on. And okay, as the next step, we are now approaching some special linear operators. So far, we have considered linear operators in a very general form. And now we're going to define some specific linear operators. So this is now section 1.22, which I call adjoints and Hermitian operators. And we start with the definition of an adjoint operator. This is definition 1.3. So let A be a linear operator. Then it's adjoint. Or Hermitian conjugate. Operator A dagger. Okay, it's defined such that for all V and W of H we have V A W is A dagger V W. Question 1.14. We're now here. This notation is the inner product. So this is a formal definition of the adjoint operator. So it's an operator, of course, on the Hilbert space on H. Okay, so this is how you actually learn it. If you do linear algebra, right? And let's see now some consequences. The first thing is that we're going to take a look at what happens if I have two linear operators acting one after the other. So let's go there. So let's say, consider now what is if A, B act on. No, say like this. If we have V and AB acting on W, okay, then we can write this as V and A acting on BW. From this we know that this is nothing else but A dagger V BW, okay, and we can now also write this as B dagger A dagger B W. And from this we find the relation that A B dagger is equal to B dagger A dagger. So this is how you calculate the Hermitian conjugate of an operator which is made out of two. Okay. And okay, now let us define that the Hermitian conjugate of a state vector is its dual vector. Yeah, what then happens, then we have if something like V W dagger, then simply W V. And if you take a look here now, A dagger V, okay, A dagger V dagger is simply VA. So what we applied is, we applied this rule and this definition, okay, in order to calculate the dagger of A dagger V. So we switch them and calculate the daggers of them. Do you see this? Okay. And then with this we can now calculate this inner product. With this equation 1.40, or both sides actually, both sides of equation 1.14 become VAW. Okay, so if you calculate here this inner product, this is an inner product. In the notation that we introduced in the beginning, this is nothing else but VAW. Okay, and what's that? This is A dagger V dagger W, and this what we calculated here, simply VAW. Okay, so we see then that there's the equality on both sides, and for simplicity, we always use now this notation for the inner product. But here I had to use the more formal notation in order to formally introduce what are Hermitian conjugate operators, because this is how they are defined, right? And then we find these properties, and with these properties we can now use this shorthand notation. Okay. Then what follows now is a bunch of definitions. And we're going to need these definitions in order to set up the language that we use, right? That you always know what's going on if we speak about something particular. So the first thing that we define are Hermitian operators. So an operator A on H satisfying A dagger equal to A is called Hermitian. Or sometimes also called self-adjoint. Then next what we need are so-called normal operators. And these normal operators satisfy A dagger A equal to A dagger. So they commute with their Hermitian conjugate. So next is a very important class of operators, I mean operator U, which U dagger U equal to identity, it's called unitary. And then we also need positive operators. So it's either called positive or positive semi-definite if for all elements V of the Hilbert space we have VH V greater or equal to 0. And we say that if A is positive, then we write it down as A greater equals 0. Okay? So this notation seems a bit strange in the beginning because A is an operator and then say operator greater equal to 0. Okay, what does it mean? It means that it's positive. That's how we express it, right? And then the last definition here, 1.8. So an operator A on H is called positive definite. If for all V of H we have V A V is greater than 0. Okay, so note the small difference. For positive operator, this inner product is always greater or equal to 0. And for a positive definite operator, it's always greater than 0. Okay, then this brings me to some remarks. The first thing is that Hermitian operators have always positive eigenvalues. So it's very easy to see actually. Sorry, not positive, I mean real eigenvalues. Not positive, sorry, with real eigenvalues. So I'd like you to prove this as an exercise. And then the second remark is that unitary operators, they preserve the inner product, and that's what makes them so interesting. So unitary operators preserve the inner product. By this I mean that for, say, phi and psi of H and U unitary, we have the following identity, the scalar product of U times phi with the u times psi. Okay, now what we do is we apply actually this rule here. It's u dagger u times phi psi. Okay, now since u is unitary, this gives the identity. So we get psi phi psi. And so this equation 1.16. So what you see here is now with the unitary we acted upon both states, but the inner product is invariant under this unitary. So, and you can now see this unitary as a transformation of the basis. So these states phi, I mean, you can always write them down as linear combination of the basis states. Okay, and then what this actually does is simply, since you do not change the overlap of the states, so to say, what you do with this unitary is you perform a basis transformation. And this is actually how you should see unitary transformations. Unitary transformation is simply a transformation of the basis. Right? And the inner product does not change if you transform the basis. Suppose, for example, that you have two state vectors which are orthogonal. I mean, if you write them down in a different basis, they are still orthogonal, right? And this is because of this relation that the inner product cannot change under unitary transformations, because it's simply a basis transformation. So, okay, this is an important property. And now I'd also like to introduce another important family of operators. So what I'd like to introduce now are so-called projectors. So we are now at definition 1.9. Okay. The projector on a k-dimensional subspace let's call this W, it's a subspace of H, and say this k-dimensional subspace has the basis W1 to WK. Is defined as P is equal to the sum of this cat brass, so to say. This is equation 1.17. So this is the formal definition of the projectors. You can take now again any basis, any ON basis, sorry, this must be an ON basis with ON basis. So you can take any orthonormal basis of your k-dimensional subspace, and if you write this down here in this outer product representation, you get your projector. And these projectors are interesting because they have very interesting properties. So the remarks first, projectors are Hermitian. So we have P dagger, let's calculate this. It's sum over J, WJ dagger. This, so we can, this is linear, so to say. And if we dagger this WJ, okay, we simply swap them. And this is P again. So we see that a projector is Hermitian. Then second, hence projectors are normal. Remember what the normal operator was? I think it's still here on the blackboard. Definition 1.5, operator's normal if A dagger commutes with A. Okay, and if A is equal to A dagger, okay, it's the same, the relation holds. So this, and since the projector is Hermitian, it's also normal. Then number 3 is, and this is a very interesting property that we're also going to use often, namely projectors satisfy P squared is equal to P. Okay, let's calculate this. What's P squared? Simply, let's plug in this definition. So we have sum over J, WJ, and then sum over, call this J prime, WJ prime, WJ prime, sum over J, J prime, WJ. So this here, remember that this W is also normal basis. So this gives us the Dirac delta of J and J prime. The Kronecker delta, sorry. Which gives sum over J, WJ, WJ, and this is our projector again. Okay, and the last property of projectors is that projectors are positive. And now remember what it means that the operator is positive. It means that the inner product of the operator acting on a vector with the vector itself must be greater or equal to 0. Let's check this. So take, say, for any v in H, we have the following, namely that v in the projector on V. Now plug in the definition, which is here, sum over J, WJ, WJ, V, which is sum over J, V, WJ, WJ, V. Okay. So these are, here's a scalar and here's a scalar. Okay. And this is the complex conjugate of this one. So we have sum over J, the modulus square of V, of the inner product of V and WJ, and this is of course greater or equal to 0. So projectors are positive. Okay, what does it actually also mean? I think I didn't mention it. Positive means also that you also only have positive eigenvalues, right? If this holds for every vector, then you must have positive eigenvalues. And the projector, the eigenvalues of a projector are either 1 or 0. Okay. We can already see this here, but we're gonna see it in detail that this is already actually the so-called eigendecomposition, and this we're gonna discuss next time. And with this, I'd like to stop here and see you on Thursday.